when you look at a massive skyscraper,
Mm.
your eyes are usually just immediately drawn to the glass, right? The glass and the steel.
Yeah, exactly. You almost never think about the rebar.
Right.
Which is funny because, I mean, the structural integrity of the entire building depends entirely on that hidden metal skeleton buried deep inside the concrete. You can't even see it.
But if that unseen framework fails, the whole tower just completely collapses.
Oh, absolutely.
Well, today we are looking at the mathematical equivalent of that hidden rebar. We're doing a deep dive into a concept that honestly dictates the dimensions of the TV screen sitting in your living room, the chemistry of the bread you bake, and far more critically, whether a life-saving medication cures a patient or becomes a lethal overdose.
Right.
Our mission for you today is mastering ratios and proportions.
Which I know might sound like a strictly academic topic, like something you'd really only encounter flipping through a TEAS or, a HESI nursing exam prep guide.
Yeah.
But this is really the hidden mathematical infrastructure of the entire world around you.
It really is.
Yeah.
And today's stack of sources pulls from, well, we've got historical math texts, clinical safety case studies, some wild statistical paradoxes, and of course, the core exam prep principles you actually need to navigate these calculations. So, okay, let's unpack this.
Let's do it.
Before we get into the literal life and death stakes, we kind of need to define the underlying mechanics, right?
Yeah, we have to start at the foundation. So basically, a ratio is just comparison of two distinct quantities by division.
Okay.
Picture a study group. Say you have 12 students and 3 tutors. The ratio of students to tutors is 12 to 3, which simplifies down to 4 to 1.
So for every single tutor, there are 4 students.
Exactly. And you'll see this written out with a colon or just with the word 2, or even as a fraction. They are all expressing that exact same physical relationship.
And then a proportion simply takes that concept a step further, right?
Right.
It's basically a statement that 2 ratios are equal at different scales.
Yeah.
Like, if you have another study group across the hall that maintains that exact same staffing structure, you can confidently say 12 over 3 equals 20 over 5.
Right.
Both of those fractions describe that exact same underlying 4 to 1 reality.
That's spot on. You have the initial comparison, and then you have the assertion of equality between those two comparisons.
Which, setting these up like little fractions sounds incredibly straightforward to us today. We just punch the numbers into a calculator and move on.
Oh, sure.
But digging into the historical sources we have here, treating these relationships as mere numbers actually triggered like one of the most dramatic crises in the history of mathematics.
It really did. To understand the sheer scale of that crisis, you kind of have to look at the ancient Greeks.
Right.
Because for about 2,000 years, starting with Euclid's Elements, a ratio wasn't a fraction. It wasn't some decimal you could just write down.
So what was it?
Well, to the Greek mathematical mind, a ratio, which they called logos, was a strictly physical relationship between two geometric magnitudes.
Oh, wow.
Yeah, they were literally comparing physical lengths or physical areas.
Wait, so they were doing this entirely without algebra. They were just physically comparing, like, the length of a line drawn in the sand to another line drawn in the sand.
Exactly. And they were forced to maintain that strict geometric approach because of a pretty catastrophic discovery.
The Pythagoras thing, right?
Yeah, let's look at the Pythagoreans. This was a school of thought organized around a central, almost religious philosophy. Their motto was basically, all is number.
Right.
Their entire universe was built on the premise that absolutely every physical magnitude could be expressed as a perfect ratio of whole numbers.
So they believed the universe was just mathematically clean. Like if you zoomed in far enough, everything would just line up on a perfect measurable grid.
Exactly. But then someone in their circle and historical tradition usually points to a mathematician named Hippasus. He discovered a flaw in that grid.
A pretty big flaw.
A huge one. He was examining just a simple square, right? And he attempted to find the ratio between the side of the square and its diagonal. What he discovered is that the diagonal is incommensurable with the side.
Meaning there is no tiny unit of measurement, no matter how incredibly microscopic, that fits perfectly into both the side and the diagonal at the same time.
Exactly. If the side is 1, the diagonal is the square root of 2.
Which is an irrational number.
Right. It cannot be expressed as a ratio of 2 whole numbers. Its decimal expansion just goes on infinitely without ever repeating. So the Pythagorean definition of a ratio, a clean comparison between 2 whole numbers, it completely collapsed when they applied it to literally one of the most fundamental shapes in geometry.
I mean, reading about this, that feels like a computer encountering a fatal error. Like the entire operating system of their universe just blue-screened because it encountered a value it physically could not process.
That is a perfect analogy.
The geometry was staring them right in the face, but their math said it shouldn't exist.
And the resulting panic was profound. I mean, legend actually suggests that Hippasus was taken out on a boat and thrown overboard by his peers just to keep the existence of irrational numbers a secret.
Wait, really? A math murder?
Yeah. I mean, while modern historians debate the literal truth of the drowning, the myth itself really illustrates the severe existential threat this posed to their entire worldview.
So how did mathematics recover from that?
Yeah.
If the basic concept of proportion was fundamentally broken, how do we have working calculus and physics today?
Well, a Greek mathematician named Eudoxus of Cnidus developed a brilliant workaround in the 4th century BCE.
Okay.
He basically created an incredibly abstract definition of equal ratios that just didn't require the underlying quantities to be measurable by whole numbers. He effectively used a concept similar to limits.
Whoa, like in calculus.
Yeah, proving that you could box in an irrational ratio between rational numbers without ever needing to define the irrational number itself.
See, here's where it gets really interesting to me. Eudoxus just bypassed the need for a perfect grid entirely. He built a working theory of proportions that handled irrational geometry perfectly.
And what's fascinating here is that his conceptual leap was literally thousands of years ahead of its time. He anticipated the rigorous definitions of real numbers that wouldn't actually be formalized until Richard Dedekind's work in the late 19th century.
Wow.
Yeah, Eudoxus basically kept the mathematical engine running.
Which is great for us, right?
Yeah.
Because the ancient Greeks wrestled with all the profound geometric implications, so that today we have the luxury of just treating these relationships algebraically.
Exactly.
When you sit down to take an entrance exam, for nursing school, you aren't drawing lines in the sand. You are just solving for a missing variable.
Right. On an exam, a proportion problem almost always provides 3 of the 4 variables in the equation. A over B equals C over D.
Yeah.
And your entire task is just finding that 4th variable. The universal mechanism for this is cross multiplication.
You just multiply diagonally. So A times D equals B times C.
Exactly. And the reason this works isn't some magic trick. It's just basic algebra.
Right.
If you have fractions on both sides of an equal sign, multiplying both sides of the entire equation by both denominators clears out the fractions completely. It takes a vertical fractional relationship and flattens it into a straight, horizontal line of algebra that is incredibly easy to solve.
Let's actually apply this mechanism to a real example from the sources. Like a map scale. You check a map legend and see that 1 inch represents 50 miles. You measure the distance between 2 cities on the paper, and they are 3.5 inches apart.
Right, so you set up the first ratio based on the known relationship, 1 inch over 50 miles. Then you set that equal to the incomplete relationship, 3.5 inches over x miles.
And then you cross-multiply.
Right, 1 times x equals 50 times 3.5, giving you 175 miles.
I mean, the math itself is basically just arithmetic. The place where test takers actually sabotage themselves is almost always in the structural setup.
Oh, 100%.
Like, consider a recipe that requires 2 cups of flour for every 3 eggs. The ratio is 2 over 3. If you want to scale up and use 5 eggs, and you set up your proportion as 2 over 3 equals 5 over x, well, your math is going to fail.
Because you placed eggs in the denominator on the left side of the equation, but then you flipped it and put them in the numerator on the right side.
Exactly. I kind of think of it like getting dressed in the dark. If you put your left shoe on your right foot, you might technically still be wearing shoes, but you aren't going to get very far.
That's a good way to put it.
Flour must occupy the numerator on both sides. Eggs must occupy the denominator on both sides. The physical units dictate the algebraic structure.
Yeah, maintaining parallel units across the equal sign is really the single most effective way to eliminate careless errors.
For sure. The source material also points out a couple of major conceptual traps, though. The first one is conflating a ratio with a fraction, which, they share the exact same notation, so it's easy to do.
They do, but they describe very different realities. A fraction usually describes a part out of a whole. So 3 slices taken from an 8-slice pizza represents 3/8 of the total object.
Yeah.
But a ratio compares 2 distinct separate groups. If a classroom contains 3 boys and 5 girls, the ratio is 3 to 5.
So the denominator of a fraction represents literally everything, but the denominator of a ratio just represents the other group.
Exactly. Now, the second major trap is the instinct to scale a ratio additively.
Oh, this one is huge.
Yeah, if someone is asked to scale up a 2 to 3 ratio, they might simply add 2 to both sides, resulting in 4 to 5.
Which completely alters the concentration of whatever you're making. Scaling must be multiplicative. You have to multiply both sides by a constant factor.
Right. And, if you make an additive error while baking, your cake is just going to be dense.
Disappointing, but fine.
Right. But this brings us to why clinical exams like the TEAS and HESI test this concept so relentlessly. Making a structural proportion error in a clinical setting has devastating consequences.
Yeah, the sources get pretty intense here.
They do. Look at the 2007 heparin overdose at Cedars-Sinai Medical Center. This was the incident involving the newborn twins of actor Dennis Quaid.
Oh, yeah. That case dominated the news cycle for months.
It was a massive story. The clinical staff accidentally administered a dose of heparin, which is a critical blood thinner, that was 1,000 times the intended concentration.
1,000 times?
Yes. The hospital stocked 2 different vials. One was an infant flush containing 10 units per milliliter. The other was an adult therapeutic dose containing 10,000 units per milliliter.
Wow.
The vials were visually very similar, and the adult vials were accidentally placed in the pediatric unit.
So the physical volume of the liquid they injected was exactly the same, but the concentration ratio was radically different.
Radically different. Thankfully, the infants survived, but the incident forced nationwide hospital reforms regarding how medications are packaged, barcoded, and stored.
So what does this all mean for you listening? Well, if you are preparing for a clinical exam, dosage calculation isn't just some arbitrary math hurdle designed to weed out applicants.
No, not at all.
It is the fundamental firewall of patient safety. You are translating a doctor's order into a physical volume of liquid.
Exactly. The standardized setup for clinical dosing is known dose per known volume equals ordered dose per unknown volume.
Okay, so if the pharmacy supplies a medication concentrated at 250 milligrams per 5 milliliters, and the physician orders 400 milligrams, you have to determine the physical milliliters to inject.
Right, and structuring that properly means milligrams over milliliters equals milligrams over milliliters. So 250 over 5 equals 400 over X.
And then cross-multiplying gives us 250x equals 2,000. Divide both sides by 250, and you find the patient needs exactly 8 milliliters.
Yep. That exact calculation is performed thousands of times a day in literally every hospital in the world.
It's vital. But I do have a question about this. I constantly hear this cross-multiply rule presented as a universal law for any 2 moving variables. But doesn't that assume a really specific physical reality? Like what happens when the variables don't scale upward together?
Yeah. That is the critical distinction between a direct proportion and an inverse proportion. Okay. Everything we have analyzed so far, the map, the recipe, the medication, has been a direct proportion. An increase in one variable forces a proportional increase in the other.
Right. More milligrams means more milliliters.
Exactly. But exam writers intentionally exploit this assumption by introducing inverse proportions.
Where an increase on one side actually forces a decrease on the other.
Yes. Consider a construction crew. Say 4 workers require 6 hours to complete a project. How long will it take 8 workers?
Right. If you automatically set up a standard cross-multiplication, 4 over 6 equals 8 over x, you will completely fail the question.
Exactly, because doubling your labor force does not increase the time required to build the thing. It decreases it.
So the algebraic structure of cross-multiplication completely breaks down there because it assumes a linear upward trajectory.
Right. In an inverse proportion, you do not set the fractions equal to each other. You set the products of the quantities equal to each other. The total amount of labor required to finish the job never actually changes.
So 4 workers multiplying their effort by 6 hours equals 24 total labor hours.
Yep. So 8 workers multiplying their effort by X hours must also equal that exact same 24 hours. 8 times X equals 24, meaning X is 3 hours.
You really have to evaluate the physical reality of the word problem before you just impose an algebraic formula on it.
And if we connect this to the bigger picture, misidentifying the underlying relationship is definitely how test takers fail. But when statisticians and researchers misidentify these relationships,
Oh boy.
they can generate massive, highly convincing statistical lies.
Which brings us perfectly to Simpson's paradox. Because how can mathematically accurate proportions be aggregated to tell a completely false story?
It's wild. The most heavily scrutinized example of this occurred at UC Berkeley in 1973, looking at the graduate school admissions.
Right.
When researchers looked at the overarching proportions, men were admitted at roughly 44%, while women were admitted at roughly 35%.
Which, I mean, a 9% disparity across a massive university system that looks like an undeniable mathematical indictment of gender bias in the admissions process.
It really does. And the proportions were mathematically accurate at the aggregate level. But then in 1975, a paper published in Science reanalyzed the exact same data set, isolating the data department by department.
And the findings completely inverted the narrative.
Completely inverted it. In the vast majority of individual departments, women were actually admitted at a mathematically higher rate than men.
Wait, how does the math actually allow for that? How can individual departments favor women, but the aggregated university data heavily favors men?
Well, it comes down to the denominator, the sample size of the underlying groups. Women were disproportionately applying to highly competitive departments like English, which had incredibly low admission rates for everyone.
Right.
Let's say a department only accepts 5% of applicants. If 100 women apply, only 5 get in.
Okay, and the men?
Men were disproportionately applying to less competitive departments, like engineering, which accepted a huge percentage of everyone. So if 100 men applied to a department with a 50% acceptance rate, 50 get in.
It's like blending two perfectly good smoothies into one giant, terrible tasting one. When you pull those two distinct realities together, the sheer volume of men being accepted into the easier departments just entirely overwhelms the data from the smaller, highly competitive departments.
That's exactly what happens. The aggregate proportion was a weighted average that heavily masked the individual departmental realities. This is a crucial lesson from the source material. A proportion is only as meaningful as the population it is drawn from.
Right. You cannot blindly aggregate ratios from distinct subpopulations and just expect the resulting proportion to reflect reality.
Never.
Speaking of human beings desperately trying to impose mathematical order where it doesn't belong, we need to address the golden ratio.
Oh, this one.
You see this everywhere in pop culture. The idea that the number 1.618 is this mystical proportion that secretly governs the design of the Parthenon, the art of the Renaissance, the spiral of galaxies.
Right, and this raises an important question about cognitive bias and pattern recognition, because when mathematicians and art historians actually rigorously analyze the claims surrounding the golden ratio, they almost universally fall apart.
Wait, really?
Oh yeah, the measurements are routinely cherry-picked.
So, like, someone measuring a classical sculpture will just decide to measure from the top of the head to the navel, and then from the navel to the floor, just to force the math to spit out 1.618.
Exactly. They just adjust their starting and ending points until they find the ratio they are looking for. There is literally zero architectural source material indicating the builders of the Parthenon intentionally utilized 1.618.
We are such a pattern-seeking species. We crave hidden mathematical infrastructure, and we will manipulate our measurements until we find it.
We really will. It serves as a great reminder to remain highly skeptical when someone uses a single proportion to argue for, like a mystical design in the universe.
Proportions are tools for measuring reality, not magic spells for altering it.
Beautifully said.
Well, we have covered a tremendous amount of ground today, tracking the evolution of ratios from ancient Greek geometry to modern statistical paradoxes. So let's distill this deep dive into 5 essential takeaways for you. Rule 1. A ratio compares distinct quantities. A proportion declares 2 ratios equal.
Rule 2. The engine for solving direct proportions is cross-multiplication. Multiplying A by D and B by C clears the fractions and allows you to solve for the missing variable algebraically.
Rule 3. Proportions scale multiplicatively. You multiply or divide to scale up or down. You never add or subtract.
Rule 4. Before you calculate, you have to analyze the physics of the problem. Is it a direct proportion where variables rise together, or an inverse proportion where an increase in one variable forces a decrease in the other?
And Rule 5, honestly, the absolute lifesaver on any exam. Maintain parallel structure. Keep matching units and matching positions across the equal sign. If milligrams are in the numerator on the left, they must be in the numerator on the right.
And, mastering those mechanics won't just get you through a nursing exam.
Not at all. You will apply this framework constantly. You use it at the grocery store to calculate unit pricing and determine the actual cost per ounce of competing products.
Right.
You use it to analyze your debt-to-income ratio when applying for a mortgage. Or you rely on it when interpreting public health dashboards that report infection rates, per 100,000 people.
Yes, to standardize the data across vastly different city populations.
The math is embedded in the infrastructure of daily life.
It is. And to leave you with one final thought that builds on everything we've explored today, consider the semantic difference between the words probability and odds.
Ooh, okay.
We use those words interchangeably in conversation all the time, but mathematically they represent two entirely different structures.
How so?
Well, probability is fundamentally a fraction. It measures the number of favorable outcomes out of the total possible outcomes. It is a part out of a whole.
Right.
Odds, however, are a ratio. They compare the number of times an event will happen directly against the number of times it will not happen.
Ah, so they compare two distinct groups, not a piece against the totality.
Exactly. When a weather forecast predicts a 75% probability of rain, that is 3 out of 4 total possible outcomes. But the odds of rain are 3 to 1. 3 chances it rains compared to 1 chance it doesn't.
Oh, wow. That completely reframes how you process risk.
It does. The numbers look different because the denominator represents a fundamentally different reality.
It all comes back to the rebar.
It always does.
The math is invisible, but it is holding up the entire structure of the world around us. Make sure your rebar is solid, and you'll navigate the data a lot more safely.
Thank you for joining us on this deep dive. Keep questioning the numbers, keep analyzing the underlying structures, and we will catch you next time.